Okay, so let's start today's lecture. So just before we start again, uh, I'd like to know what you remember from the last class. So what all topics we discussed in the last class? Okay, so we discussed about branch prediction. Mainly, we were discussing about control hazards, and as part of control hazards, we discussed about a very important concept as called as branch prediction. Now, why is branch prediction used? Why is branch prediction used? What is the need for branch prediction? So in the case of control hazards, you have seen in the last class that the execution might have some delays. The reason is the branch will be evaluated only at the end of EX stage, and you might want to fetch the instruction much before that. So hence, if you have a branch, every time introducing a delay is not a very good idea. So that is why you use a technique called as branch prediction, where we predict the outcome of the branch before itself, and if the outcome is same as the prediction, the actual outcome is same as the prediction, then you don't have to worry. But the actual outcome is different from what you have predicted, then only there might be a delay. Okay, so and we have also seen branch prediction techniques. So what is the main classification? How are branch predictors classified? Main classification, and then we'll talk about sub classifications. So main classification is you have a static branch prediction and dynamic branch prediction. So what do you mean by static branch prediction? What do you mean by static branch prediction? So it's like you always do a fixed prediction. Okay, so you either predict that the branch will be taken always, or you predict that the branch will not be taken always. Okay, so that is like you're fixing the prediction, and you'll always be predicting only one thing. It's like a constantly will be predicting the same thing. Okay, that is static prediction. And what about dynamic? What do you mean by dynamic branch prediction? So dynamic branch prediction, what is the basic idea of dynamic branch prediction? So the dynamic branch prediction is a case where you predict the branch behavior, okay, based on something, typically based on previous predictions. Okay, so based on some algorithm. It might not always be previous predictions. It might be sometimes it might be implementing some algorithm and so on. But here we are assuming that based on the previous outcomes, based on the previous outcomes of that particular branch, we'll be predicting the new branch condition. Okay, so that's basically dynamic branch prediction. Okay, so in the how is it implemented in the case of dynamic branch prediction? You have something called as a branch history table. You call it as a branch prediction buffer also, but most of the books use this terminology. Okay, so they term it as BHT. Okay, so branch history table will be there, where you will be. It's what is a branch history table? What is branch history table? I think we discussed this all in the last class. What do you mean by branch history table? What is it? Is it like some combinational block? Is it like a sequential block? What is it? It's basically a memory. Now, again, the one bit memory or not, that's a different question. Okay, so its first thing is it's a memory. Okay, now how do you access this memory? So what will be stored in this memory? First thing, so the values that will be stored in the memory. What values will be stored in the memory? So here you have to remember here states will be stored. Okay, states. So based on this states, the prediction will be done. Okay, so we talked about last class. We talked about one bit prediction. Okay, one bit prediction had how many states? So we said that let's say S naught, we'll assume that this is a taken state, hence your output is one. And then we said that there was another state which will always which will basically predict that the output will not be taken, and then you will be having a zero. Okay, so here this zero or one basically represents the state, okay, either this state or this state. So based on that, you will be predicting something. Okay, if it is zero, the prediction will be not taken. If it is one, the prediction will be taken. Now, how do you change states? Okay, let's say I was like when you say zero, I'm saying that I'm there in this state. Okay, so sorry. Okay, so whenever something 0 is stored, okay, let's say 0 is stored in this location, it basically means that I am in this state now. Okay, now relay some branch has to access this memory for getting the prediction. How does branch access this memory? How will the branches access this memory? So when you say predictions are stored as a memory, you have to access this memory, right? How do you access this memory? That also we discussed. Using address. Using which address? Lower address bits. Which lower address bits? The lower address bits of instruction. Which instruction? The lower address bits of the branch instruction. Okay, so let's say there is some branch and it will be having some address. This instruction will be stored at some address. The lower bits of this address will be used to access this memory. And let's say some branch is there which is accessing the first location. Okay, when it sees that the branch is accessing the first location, it will see a 0 and it will predict that the branch will not be taken. Okay, because it is 0, it is assumed that the branch prediction will be in this state. Okay, it will predict that the branch will not be taken, but the outcome came different. Okay, the actual outcome, which you will be able to know at the end of EX stage, actual outcome is something different. Okay, let's say in that case, the branch was supposed to be taken. Now, what will happen? What will happen to this value? That depends on the state diagram. Okay, so we have also drawn the state diagram for 1-bit branch prediction. How does it look like? So if you are in this state, if the prediction was true, meaning if the outcome was also not taken, okay, then you remain in the same state itself. But here the actual outcome is different. Okay, in that case, what should I do? The actual outcome is different. So in that case, what should I do? What should I do? I should change state. So if the outcome is different, if the outcome is taken, then you have to go to S0 state. Okay, so this is happening here. So once it goes to S0 state for that particular branch, you have to change the data that is stored. Okay, so here instead of 0, you have to replace it with a new state. Okay, you have to replace it with new state, that is 1. Okay, so earlier it was 0, now it will be 1. So like that, this state diagram will decide what will be stored. Okay, remember, I am not storing the actual whether it is taken or not taken. I will be storing the states. So in 1-bit prediction, hence the value that I will be storing is 1 bit. Okay, that 1 bit will indicate which state am I currently in. Okay, and with the help of that state and with the help of the outcome, you will decide whether to make sure whether to remain the same state or change the state. Okay, so accordingly your prediction will be done. Okay, and again we have already completed the state diagram, so again you will remain the same state if your outcome is taken, but if your outcome is not taken, okay, outcome is not taken, then you change the states and go to let's say S1. Okay, in S1 again you keep predicting, you store 0, and 0 basically means that you'll be predicting that the branch will be not taken. Okay, so these things we have discussed in the last class. Okay, so a small memory will be indexed by lower portion of the address of the branch instruction. The memory contains bits that will be used for prediction. Okay, the memory contains bits or bit that will be used for prediction. Okay, so in 1-bit prediction scheme, how do you what exactly is stored depends on the state, and we have already understood the state diagram. It basically check if the branch was taken last time it was executed, and based on that the new prediction will be done. So you basically have to follow the state diagram that I showed. Okay, so now I asked again, this is basically about 1-bit prediction scheme. Okay, and one more important thing is what was the problem? The problem was multiple branches may index same entry. Okay, why will this happen? So we talked about this issue also in the case of branch history table. Why do you think this will happen? So I gave you some example also, right? So what do you mean by this statement? Multiple branches may index same entry. So lower addresses, okay, lower addresses bits that are used for accessing the branch history table might be same for 2 different branches. Okay, the branch, the address bits, the lower address bits which are used to access the branch history table might be same for two different branches. So normally what happens, the actual number of branches will be in hundreds, thousands, or something like that. Okay, it will be in terms of hundreds and thousands if you talk about an application. But the actual number of the actual locations in the branch history table will be limited. Okay, maybe 1024 or maybe 2048. Okay, so in that range, or 4096. So it will be very limited. Okay, the values, the locations that are available in your branch history table will be very limited, whereas the number of branches will be very large. So in that case, there is always this case where multiple branches might access the same location, and they might change the next prediction for a different branch. But that will not cause a problem, as I will be showing with some statistics next. Okay. But before that, we'll be discussing the 2-bit prediction scheme. Last time I asked you to come up with a state diagram for 2-bit prediction scheme. Did anyone try? So how will this 2-bit prediction scheme work? So I talked about briefly this also. So in 1-bit prediction scheme, you change the state. So you change from 0 to 1 or from 1 to 0. In what case will you change? You change the state from 0 to 1 or 1 to 0 when? When you get how many false predictions? Just one false prediction? In the case of 1-bit. In the case of 1-bit prediction, you change the state as soon as you get one wrong prediction. So you are actually predicting the branch will not be taken, but immediately if your outcome is that the branch is supposed to be taken, you immediately change states. Okay. So this is for a 1-bit prediction scheme. But for a 2-bit prediction scheme, you change your prediction. Okay, you change your prediction from not taken to taken only if the prediction is wrong twice. Okay, prediction is wrong twice. Only then you change the prediction from not taken to taken. Okay, so that's the idea behind 2-bit prediction scheme. Consecutively wrong. Yes, consecutively wrong. Okay, maybe I did not reiterate that. So you change from not taken prediction to taken prediction only if the prediction is wrong twice consecutively. Okay. So if that is the case, how does the state diagram look like? So there were two implementations that was given. So prediction must be wrong twice before it is changed. There are two types of prediction schemes here. Okay, two type of 2-bit prediction schemes are available. Again, you know that we are trying to implement a state machine where the input for the state machine is the outcome, and based on the present state, you'll be predicting. Okay, so based on your outcome and based on what is supposed to be there, you'll be coming up with some kind of prediction. Okay, so this is how the state machine looks like. Now let us see the first scheme. So the first scheme is a 2-bit prediction scheme, which is based on saturation counter, which was proposed by J. Smith in 1981. Okay, so here the state diagram would look like this. Okay, let's say I'll start my state with not taken. I'll initialize my memory. One thing is, in the case of 2-bit prediction scheme, each memory location will be how many bits? Each memory location will be how many bits? I think we discussed this also. So each memory location will be 2 bits. So based on these 2 bits, you will make a prediction. Okay, but when you say 2 bits, there are 4 possible cases. Okay, but what each of this possible case means, so that is what your state diagram will identify. Okay, so now we'll start with the state diagram. Initially, I'll say I'm predicting not taken. Okay, now what if my outcome is also not taken? Okay, so this was my prediction and your outcome was also not taken. What will happen? You stay in that. Okay, you stay in that state only. Okay, so if your outcome is also not taken, so whatever I am specifying on the edges, so they are basically outcomes. Okay, just remember that. Okay, so outcomes are represented on edges. Okay, in the state diagram. So you stay in that. Now, if the prediction was wrong, okay, so what will I change my state to? Or what will I predict? Okay, what will I predict? I will predict that it is not taken, but should I remain the same state? So what will this state indicate? This state indicates that my prediction is correct. Okay, this state indicates that my prediction is correct. Now I have to come up with another state which will tell me that the prediction is wrong once. Okay, but I'll still predict what? Even if it is wrong once, what will I predict? Will I predict that the branch will be taken or not taken? I'll predict that the branch will not be taken, but I should somehow know that last time's prediction was wrong. Okay, how do I know that? So will that happen if I remain in the same state? It will not. So I have to define one more state which will tell me that the prediction was wrong once. So here also I'll predict not taken only, but the state is different. Okay, so now 0, 0 indicates that my predictions were correct. Okay, with respect to not taken, but now 0, 1 will indicate that my prediction of not taken was wrong once. Okay, my prediction of not taken was wrong once. Okay, so that is what this 0, 1 state means. Now let us say you are in this state. Now the prediction has come true. Okay, meaning your outcome is also not taken. If you are in this state, your outcome, let's say if it is not taken. So what will that mean? What will that mean? Your prediction is again correct. So if your prediction is correct, what should I do? Should I remain in the same state or should I go to the original state 0, 0? So somebody is saying stay there. Why should I stay there? So what, again, I just told you, right? What does 0, 1 state indicate? So 0, 1 state indicates that my prediction of not taken was wrong once. But now it has again correct. Now it is again correct. Okay, now if it is correct already, then I have to go back to my original state. Okay, so that is why here if the outcome is not taken, I'll go back to original state. Okay, 0, 0 state. Okay, now if you are in this state and if your prediction and you are predicting that the branch will not be taken, but the outcome, you found out that the branch is supposed to be taken. So in that case, what should I do? What should I do in that case? Which state should I go and what should I predict? So you tell me, what should I predict next? So if my current prediction was wrong, next time what should I predict? I should predict that the branch will be taken or not taken. So now I have to predict that the branch will be taken. Okay. So here till this point, it will be same for the two different schemes. I told you that there are two 2-bit prediction schemes. Okay. So the difference will start coming here. So in one of the prediction schemes where the prediction scheme uses something called a saturation counter, I'll tell you why this is called a saturation counter later. Okay. So once you found that the branch outcome is false, meaning the outcome was not correct. Okay, your prediction was wrong when you are in this state. So that tells you that the prediction is wrong twice. So once the prediction is wrong twice, what I'll do, I'll go to another state. Okay, I'll name it as 1, 0, and here I'll start predicting that the branch will be taken. Okay. So this is how the state diagram looks like. So if the prediction is wrong twice, then I'll go here and I'll start predicting taken whenever I'm in this state. Okay, now in this state also there are two possibilities. So your outcome is, if your outcome is taken, what should happen? If your outcome is not taken, what should happen? Can you tell me? If your outcome is not taken, what should happen? So again, we here in this case, we define something called as strong and weak. Okay, so this is like a strong state and this is like a weak state. Okay, this is a strong state and this is a weak state. So here there is slight differences. Okay, so here what happens is whenever you are in the strong state, you have to be wrong twice to change states. Okay, but whenever you are in weak state, you have to be wrong only once. Okay, so that's the basic idea. So here, if I am wrong once, I am going to this state. So this is also a weak state. Okay, so this is also a weak state in this prediction scheme. So in this scheme, this is also termed as weak state. So if the branch is not taken, if it is wrong, then I'll go back to not taken state only here. Okay. Okay, not taken state only. This is how the saturation counter works. So there is another scheme which will follow another technique which I'll show later. And then if it is taken, then you go to 1 1 state and start predicting taken. So this will be the strong taken state. Okay, so this will be the strong taken state. This will be the strong not taken state. These two are the weak states. Okay. Now here, once I go to strong state, again the analysis remains the same. So if it is taken, if the outcome is taken, you remain in the same state. If it is not taken, you go back to 1 0 state and keep on continuing. Okay. So this is how the state diagram for a 2-bit prediction looks like. Okay, so we gave initially one definition, but that is not getting satisfied here. So can you tell me, where is it not getting satisfied? Where is it not getting satisfied? So initially, let's say I start predicting that the branch if I'm in this state, let's say I'll start predicting that the branch is supposed to be taken. Okay, but as soon as I get a wrong prediction, let's say the outcome is taken, not taken. Okay, then I immediately change states here. Okay. So the initial definition of our outcome being like our prediction being wrong twice before I change states is not valid for weak states. Okay, so these are called as weak states, whereas these are strong states. So this is where our earlier definition is applicable, where we change the prediction only if our prediction is wrong twice. Okay, so this is one of the techniques that is followed for a 2-bit prediction scheme. Now, can somebody tell me why is it called a saturation counter? First of all, why is it called a counter? Why is it called a counter? Any idea why is it called a counter? You see, analyze this. Okay, so the answer is in this slide only. Each wrong prediction, will it increment by 1? Is it always the case? So here, let's say I am in 1 0 state. If I get a wrong prediction, I'm actually decrementing. No, I'm not incrementing. So again, if I'm in the 1 0, if the prediction is not taken, which is wrong, so I decrement, not increment. And similarly, if I am 0 1, okay, if my prediction is wrong, that is, if I say not taken, that it will increment, not decrement. So it is actually behaving like a up-down counter. Okay, it is actually behaving like a up-down counter. Okay, when will it count up and when will it count down based on this state table? Now let's say initially it is 0 0. When will it become 0 1? So initially I am predicting not taken. When will it increment? When will it increment to 1 0? When will it increment to 1 1? When it is taken. If you are saying that I mean not taken, whenever the outcome says not taken, you increment here. Whenever the outcome says taken, you increment. Whenever the outcome says taken, you increment. So whenever the outcomes are taken, you keep on incrementing the count. But when do you decrement the count? Let's say I'm in this state. Okay, that is a 1 0 state. If the outcome is not taken, what will I do? I'll decrement. So I'll go from this state. So if I'm in 1 1, I'll go to 1 0. If I'm 1 0, I'll go to 0 1. If it is not taken, if the outcome is not taken, and I'll go from 0 1 to 0 0 if the outcome is taken. So if it is taken, your counter is counting up. If the outcome is not taken, the counter is moving down. Okay, so that is why we call it as a counter. Now tell me, why do I call it as a saturation counter? So counter you understood. So it is counting up or down based on whether the outcomes are T or NT. Okay, so that is about the counter. It's like up down counter. So you keep on counting up whenever the outcome is taken. If you keep on counting down whenever the outcome is not taken. Okay, so it's called a saturation counter because your count stops at 1 1 or 0 0. Let's say I'm in this state. Okay, I'm in the 1 1 state. I'm in this state. Okay. Now here, if the outcome is T again. Okay. Normally in up down counter, what happens? If you are in count 1 1 and if you count up, what should happen? You know, your normal counter that you might have studied in your digital design. If you count up again, it will go to 0 0. But that does not happen here. Okay. If the T comes again, it is supposed to up count, but it will not up count. It will saturate at 1 1. Similarly, while down counting, whenever you are in 0 0 state and if your outcome is not taken, it will saturate at 0 0 only. It will not go back to 1 1. So that was also what we have seen, right? So if your value is 0 0, and if you down count in your normal binary counter, it will go back to 1 1. But here it will not happen. If your outcome is not taken again, it will not move. It will saturate in 0 0 itself. Okay, so that is one of the that's the reason it is called as saturation counter. Okay, so most of the 2-bit prediction schemes that are available in today's processors, branch prediction schemes that are available in today's processors, follow this technique, okay, which is called a saturation counter. So whenever you read something called a saturation counter with respect to branch prediction, it is basically talking about this. Okay, so now you have understood why is it called as counter, why is it called a saturation counter, and how exactly the state changes happen. Okay, now whenever you say that I have a branch history table, okay, for specific addresses, so let's say there will be many entries, and these entries will be accessed by addresses of instruction addresses of the branch instruction. Now here 2 bits will be stored. Okay, so 2 bits will be stored. So based on these 2 bits, okay, so there are many possibilities, right? Based on these 2 bits, the prediction will happen. Okay, so if it is 0 0, the prediction will be not taken. Okay, here also it will be not taken. Here it will be taken, and here it will be taken. Now, based on these predictions, it's not just enough if you analyze the predictions. You have to check the outcomes also. So I'm predicting that the branch will not be taken, but for this case, let's say the branch was supposed to be taken, the outcome came to be taken, then you have to modify this state. Okay, now you change the state from 0 0 to 0 1. So even in 0 1 case also, it will predict not taken, but it's a different state. Okay, so based on this, you will be able to modify the data that will be available in the memory. But it technically doesn't work on a 2-bit prediction scheme because it goes to 0 1 state from 1 0 state upon not taken state. It goes to 0 1 from 1 0. No, I did not get you. Can you elaborate the questions, Sargunpreet? Technically, does not
So
work.
here,
Yeah.
yeah. So when we are in 1 0 state, so we are predicting that the state is taken. But if we get a not taken state, then on one wrong prediction, it's going back to the previous state of 0 1, right?
Yeah, that's correct. So the original definition will not be valid for these states. I told you, right? I explained that also. The original prediction where we say that the prediction has to be wrong twice before it changes the prediction will not be valid for weak states here in this technique. Is it clear? So it basically changes on how, so you are initially storing 0 0. So meaning you are in this state and your outcome came to be taken. Okay, if your outcome came to be taken, then the state that you have to go is basically 0 1. Yeah, here it can go continuously wrong also. And continuously going wrong, it's depending, if your branch behavior is totally different from what we are predicting, then there is always chance of your prediction going wrong. Okay. So this was one variety of a 2-bit prediction scheme. Okay, and then the other scheme, which coincidentally was invented by another Smith. It's not the same Smith; it's another Smith. Okay, so here it's slightly different. Okay, so here again you initially start with predict not taken, and again the initial part is same. So if it is if the outcome is not taken, okay, again here outcome I am representing on edges. Okay, so if the outcome is not taken, you remain in the same state. If the outcome is taken, then you change states. So this is like a weak state. Okay, this is like a strong state. Okay, so now if you come here, here the differences will start coming. So here again, if the branch is not, if the outcome is not taken, then you go to the original state. But here, if the prediction is again wrong, okay, so now the prediction is wrong twice. So I have to start predicting that the branch will be taken. Okay, so now the branch will be taken can be, it's possible that you either go to weak state or strong state. So earlier what we did, when you were in 0, 1 state, when you were in 0, 1 state, if the prediction was taken, then you moved to which state in the earlier state diagram? You moved to 1, 0. Okay, so here you will move to a different state. So here, if it is wrong, you will move directly to the strong state. Okay, you will directly move to the strong state. Okay, so and again, once you are in the strong state, the original definition will apply again. So if it is if the outcome is taken, okay, this is your strong, okay, this is your strong, this is your weak, and then other weak state will come. So you go directly to 1, 1, and when you are in 1, 1, if the outcome is taken, you remain in the same state. If the outcome is not taken, then you go to weak state here, and then again, if it is taken, you come back. But again, if you are in weak state, okay, so and if the prediction, if the outcome is not taken, okay, you are in weakly taken state, but your prediction is not taken. So where will you jump? So you jump to 0, 0. Okay, that's the difference. So in this state diagram, your original definition is valid. Okay, you analyze in whichever you want. Okay, so I think your prediction will be again. Sorry. So when you are in strong state, you require 2 states to change your original prediction. But if you are in weak state, you will only require 1 wrong prediction to change. Weak state here basically indicate that you are already wrong once. Okay, wrong once here. So this also indicates that you are already wrong once. Okay, so that is how you will be able to analyze. Okay, so this is another state diagram. So the difference comes here. So from 0, 1 to 1, 0, if you do the transition on your wrong prediction, then that is basically the other state diagram. So this is like I'm parallelly transitioning from 0, 1 to 1, 1. Assuming that 1, 1 is indicating the strongly taken state. Okay, this is another state diagram that is typically used in 2-bit prediction schemes. Okay. So any doubts you have in this 2-bit prediction schemes? So the basic thing that you have to understand is there is in 2-bit prediction scheme there could be two different variations. Okay, so I have explained about those two variations. One is like a saturation counter. The other one is first thing is called a saturation counter. Here, it's like up down counter. Here it is, the behavior is slightly different. Okay, so from weak state, in the earlier case, from weak state, the transitioning happens to another weak state. But here, from weak state, the transitioning happens directly to the strong state. Okay, so that's the difference between these two state diagrams. But most of the textbooks, whenever they talk about advanced branch prediction schemes, and if they say that they use 2-bit prediction scheme, they will usually be talking about saturation counter based designs. Okay, saturation counter based designs is what they will be discussing about. Okay, so for a 2-bit prediction scheme, each entry in the branch prediction buffer, meaning the branch history table, will contain 2 bits. So first thing is how many such entries should be there, and is 2-bit predictor enough? Okay, so that's one question we might have. So people have run some benchmarks applications on these branch predictions, and they have come up with these this analysis. Okay, so you carefully observe what this is trying to tell you. So one analysis they have done is with limited number of entries. Okay, so there are only 4096 entries. Okay, what does this tell you when I say 4096 entries? So this conveys a lot of information. So can you tell me what all information does this convey? So what do you mean by 4096 entries? So you have a branch history table, okay, with 4096 entries. Okay, 4096 entries will be there, and it's 2 bits per entry. Okay, so there'll be 2 bits per entry. So if you have 4096 entries, so you will require 12 bits to access this particular branch history table. Okay, So you will be using the lower bits to access lower bits of the instruction address to access this particular table. Okay, so that will tell you you'll require 12 bits to access this table. That is one information. And each entry is having 2 bits because you are talking about a 2-bit prediction scheme. Okay, so this is the information that is conveyed by the first information, the first entry. But the second entry, the second branch prediction that they have used uses unlimited entries. Now, what do you mean by unlimited entries? And this is done for a specific benchmark. So there are many benchmark applications like these. Again, you can check what these benchmarks actually mean. Okay, for example, GCC is a C compiler. Okay, and you might have some matrix multiplication, 300 cross 300 multiplication. So for all of these cases, they have compared a 4096 entry branch history table with a unlimited entry table. So can you tell me what do you mean by unlimited entries? What do you mean by unlimited entries? Unlimited means sufficient memory for all branches. So can you tell me what do you mean by unlimited entries? It will be equal to what? It will be equal to number of branches. Number of branches in a given application. Let's say this application you take. So here, let's say I have maybe 20,000 branches, and here I might have 40,000 branches. Just for an example. Okay, so it basically means that whenever they test this application, they implement a table which has 40,000 entries. Whenever they implement this application, they have a branch history table which has 20,000 entries. Okay, just for an example, I'm giving these numbers. So when they actually tested it, they found out that having unlimited entries is as good as having 4096 entries. Okay, so if you see that this is giving you the frequency of mispredictions. It basically tells you if there are 100 branches, out of them only 10 are wrongly predicted. So if you, whether you have 4096 entries or whether you have unlimited entries, you see that more or less the misprediction, okay, is almost the same. Only minor differences is there. So here, in some cases, actually, unlimited entries itself is giving you worse results. Okay, because the one branch changing the other behaviors branch is giving you better results. I'll tell you the reason for it maybe in the next slide. Okay, so if you see here, okay, I think maybe we are talking about misprediction. So if you see that misprediction is better, always better in, yeah, sorry, it's my mistake. So it's in cases where there is a difference, having unlimited entries is slightly better. Okay, so only slightly better. So there is only 1% difference, but in all the other benchmarks, it's almost the same. Only in few cases, this case, and this case, having unlimited entries is slightly better. Okay, so what does this tell you? What does this information tell you? So this basically tells you don't have to have a table equal to the number of branches. Okay, so you don't have to have a branch history table with the number of entries to be equal to number of branches. It's not actually worth it because the additional benefit that you get is very less, and only in some applications you get the additional benefit. So that is why in most of the cases you go with this 4096 entry table with a 2-bit prediction scheme. Now the question comes whether 2-bit prediction scheme is enough. Okay, because it is only keeping track of last 2 branches, right? Last two outcomes it is keeping track of, because last 2 times it is wrong, you change the next prediction. So it is only keeping track of last 2 outcomes for that particular branch. So what they did, they have run another test. Okay, so prediction accuracy for a 4096 entry 2-bit prediction scheme buffer for the spec 89 benchmarks that they have run. And if you analyze, as we have seen, so the branch prediction misprediction is at the max 18% only. Okay, meaning 82% of the time your branch prediction, which is a 2-bit prediction, is giving you good results. Okay, 82% accuracy it is giving in prediction. So that is good enough, right? If you have a predictor and if you are predicting, imagine predicting correctly 82 times out of 100. Okay, that's a very good prediction scheme. If you use this prediction to maybe for some kind of betting, then I don't know, maybe you'll become a billionaire. Again, don't use it. Okay, so It might not work there. But at least for these spec benchmarks, if you see, the worst case is 82%, and the best case is you will get almost 100% or 99% accurate predictions if you use only 2-bit prediction buffer. Now, a 3-bit prediction might give you better results. So what do you mean by a 3-bit prediction scheme? Can you tell me? So let's say saturation counter. Okay, saturation counter is what I'm trying to use. So how many states will be there? It will have 8 states. Okay, that is one thing. There is one complexity in making the prediction. What is the other complexity of having a 3-bit prediction scheme? The memory requirement. Okay, if you are using a 4096 entry table and if you are using a 2-bit prediction scheme, so each entry will be 2 bits. So totally you will be using how much? Can somebody calculate this? So 4096 into 2 is 12 plus 2, 14. So how are those 4096 entries selected out of many branch instructions? I told you, right? Okay, so this is 8192. Okay, so how is, if you have 4096 entries? Okay, so how is each entry accessed? Again, it's the same thing. So there will be some instruction, right? Branch instruction. It will be having some address. Okay, this instruction will be stored in some address. So the lower 12 bits of this address will be used to access this table. Each branch instruction will have some lower 12 bits. And again, when I say lower 12 bits, what do I mean? So in the case of RISC-V or MIPS processor, if you say that from 0, 1, 2, 3, 4, and 31 is basically your instruction address, okay, the last 2 bits anyway will be 0, 0. They will not convey any information. So you have to start from 12, start from second bit and go on till maybe how many? 11, maybe 13th bit. Okay, so 13 is to 2 bits of the branch instruction will be used as address for this. No, that's what. It's nothing to do with the millions of branch instructions. It has to do with the address. So how many ever instructions be there? Okay, so how many ever instructions be there? That branch instruction will have some instruction address, right? What if we have multiple applications running? Won't have only 4. Multiple applications running is again a different scenario. Okay, so that is like a context switch. So that is totally different. Normally, when you switch between one application to another application, your branch history table that you would have stored will also change. Okay, so when you start a new application, your branch history table will reset, and then again you start loading your branch history table. Okay, so I hope I have answered your question. So first thing to understand is, let there be million instructions, million branch instructions. Okay, it doesn't matter if you have 4096 entry table. If you say that I'm using 4096 entry table, what it basically means that there might be many branch instructions. Okay, many branch instructions. But what I am concerned about is how is this getting accessed? So this will be accessed by second bit till 13th bit. I think that is 2. Yeah, so 13 is to 12. Okay, bits of the instruction will be used for accessing this particular data. Okay, so for those million instructions, sometimes these bits will be different and sometimes these bits will be same. So that's what I explained last time. If these bits are same, 2 branches might be accessing the same entry and they might modify that data. But even then, it will not create any problem. As we have seen the benchmark results, it will give you a good prediction accuracy even in those cases. Okay. I hope I have answered your questions, Sir Gunpreet as well as Amrita. So when you switch applications, typically there are 2 possibilities. One is you reset your branch history table. You initialize your branch history table such that some preloaded data will be available. And then you start loading the data based on your outcomes, your predictions, and so on. Or you entirely load a preset value, which is fixed. Okay, so you might have to store some fixed amount of fixed predictions when you load when you switch to a different application. But most of the cases they don't do that. They don't maintain a separate table, so they just reuse the same table. Okay, so after a few runs, it will automatically the behavior of this branch history table will automatically be adjusted to a new application. Okay, because you'll be not running once or twice, you'll be running this for you will be accessing this table for multiple times. So over a period, okay, the accuracy will be close to whatever we have seen in those applications. Okay, so somewhere between 80 and 90 is what we'll get in today's prediction schemes. So every time you start an application or just reset, so some preloaded data will be there. So most of the cases we assume that every entry will get initialized to some data. Okay, so let's say for our example, all entries might get initialized with 00 initially. When you reset, when you start, or when you, let's say, shut down your computer or reset your computer, you can always assume that initially all states will be reset to one of the states. So it could be as simple as initializing to 0 state. But don't focus on this. Okay, so this is like only one time, but over a period, when you run an application, okay, there'll be many branches running many number of times. So over a period of time, the branch prediction accuracy will be good. Let's say if you run your if you initialize the data and run only a few branches, let's say I just run 2 branches or 10 branches, the accuracy will not be good. Okay, when you talk about an application, okay, when you talk about an application where many branches will be running, multiple branches might be accessing the same data. When you think of that scenario, overall the branch prediction accuracy will be very good. Okay, so that's basically the idea of branch predictions. Okay. So again, in addition to this basic branch prediction schemes, whatever I discussed now are the basic prediction schemes. So in today's processors, they have much more advanced schemes. For example, if you take this scenario, okay, so I'm just representing it in high level language. So if A is equal to B, you initialize A to 0. If B is equal to 2, you initialize B equal to 0. And let's say if there is another condition, if A not equal to B. So can you tell me if these two branches are not taken? Okay, or yeah, if those two branches are not taken, what will that tell you? So if branches B1 and B2 are both not taken, meaning A is yeah, so if A is not equal to 2 and if BB is not equal to 2, then we can say that the branch B3 will be taken. Okay, so behavior of branch. So here the behavior of this branch is correlated to these two branches. Okay, so that's what we call it as correlation. Okay, so the branch B1 and B2, based on whether both are taken or not taken, based on that we can talk about the third branch behavior. Okay, so in that case, so we might use another type of predictor which we call it as correlating branch predictors. So this is a bit advanced topic. I will not be covering that as part of this computer architecture course. Okay, so there is another predictor called as correlating predictor, where it will keep track of not just itself, they'll keep track of other branches also. Okay, they keep track of other branches, and based on how other branches are behaving, so the prediction for this branch will be decided. Okay, prediction for this branch will be decided. Okay, so that is called as correlating branch predictor. And you have much more advanced predictor, which they call it as tournament predictors. So here the idea is you have two predictor. Maybe one predictor is your original predictor that we talked about. Okay, so we can call this as local predictor, where we whatever we discussed earlier, so we'll call them as local predictor. And whatever we talked about here, okay, so this we can call it as correlating predictor. Now we'll use both of them, okay, and we use something called as a selector. So now this selector, what will do? It will basically select either this predictor or this predictor for prediction, okay, based on which is behaving better. Okay, it's like another level of prediction you are trying to say. So this selector is nothing but another predictor. Now what is this predicting? What is this predicting? Any idea what will this predict? So at one level, you have a local predictor, which we discussed till now. At the other level, you have a correlating predictor, which is predicting the branch uh, based on the previous branch behaviors. Then I'll use some kind of a selector. So this was also a predictor. So what will it predict? Any idea what will it predict? Any idea what will it predict? Okay, maybe I am not clear enough. Okay, so what I said is it will select the prediction to either come from this. Okay, so either the prediction will come from this. Sorry, happened. Yeah. So the prediction will either come from this predictor or this predictor based on some. Yeah. So what this second level of predictor do? It will predict which one would result in better prediction, either to choose local predictor or either to choose correlating predictor. So that will be decided by this selector. You can think of selector as another predictor which will predict whether the first predictor will give you better result or second predictor will give you better result, and based on that it will make a decision. Okay, so don't worry about that. It is a little more complex than the predictors that I explained, but you only understand that there are much more advanced prediction schemes that are available. Okay, branch prediction scheme is a very powerful technique, and a lot of research has happened in this. Okay, we might think that it is a very small thing, branch. You are just evaluating condition, based on that condition you are jumping to some location. That's the simplest behavior of a branch. But the research that has been done in this branch predictors itself is a very big topic. Okay, so people have written thesis on just the branch prediction schemes only. Okay. So that's the importance of branch predictions. So that's why I spent some time on this branch prediction schemes. Okay. I think with that I'll stop. I think I'm out of time. I somehow did not realize the time, so it's already 4:50. Okay, so I think I've spent a lot of time on these branch predictions than I normally do in the previous semesters. Okay, so I hope you have understood the complete concept of branch prediction now. Okay. So in the next class, whatever is covered till Friday's class will be there for your syllabus. Okay, so till Friday's lecture. So there is like the small topic that I'll cover on Friday, which is how to modify your data path. The data path that we had discussed for single cycle, we'll discuss how do you modify the data path for pipeline processor, and we'll just try to understand the hazards that we discussed. Okay, we discussed about data hazards and control hazards, right? We'll discuss the same things in little more detail, and we'll get some visualization on how actually things happen in hardware. Okay, that visualization we'll try to get in the next class. Okay, so till that point it will be there for your midterms. Anyway, I'll put up official notice on Friday, but since you asked, I'm telling you it will be till whatever I cover in the Friday's class. So that will be the portion for your midterms. Yeah, it will be there. It may be there. It's not out of syllabus. It will be still part of the syllabus. So coding questions, meaning it will be based on the RISC-V ASA instruction set. So some questions might be there with respect to program. Okay, so any other questions you have? Yes.
A little off topic, sir, but in say a superscalar autoencoder processor with multiple fetching units.
Again, it was not. It was there was some connection issue. I did not hear the question properly. Can you repeat?
Sorry. In a superscalar autoencoder processor, sir, with multiple fetch units. What if you encounter a branch? What if one of the fetches units take care of the follow-through code and the other takes care of the target address? And when you know the branch outcome, you can flush one of the instructions, whether the follow-through or the this thing.
See, the point of having multiple fetch units is that you will be able to execute multiple instructions at the same time. Fetch two
Yes, sir.
instructions at the same time, decode two instructions at the same time. But if you are spending that resource for a single branch, then it's like you are wasting the resources, right?
Okay.
Okay, so there also the branch prediction will be implemented. You can't
Okay.
have a processor today without branch prediction.
Okay.
So some
So,
kind of
so I
prediction
was
is still
thinking,
used. Hmm.
yes, sir. I was thinking analogous to the carry select adder. Like me
Hmm.
and Amit were talking about it, and he was on the
Yeah,
set. Why
I
not
got it. I got it. Like you compute the result for both the
both
cases,
of them?
and then again
Yes, sir.
that is implemented, but not in normal processors. They use this concept in vector and GPUs
Okay.
to fast the processor to make the execution a little bit faster, because there the number of units are available will be huge. So if you
Yes, sir.
talk about 4 cores being available in normal processor, there you will have smaller cores, maybe in terms of hundreds or thousands,
Yes,
small
sir.
cores. So there they do this. Okay, they compute the result for both the conditions, and then take the path based on whichever condition was true. Okay, but in normal
Yes, sir.
processors, they don't do that. They don't compute both the cases. They use the branch prediction.
Okay, sir. Got it. Thank you, sir.
Okay. Okay, so if there are no questions, then I end the recording here.